think everybody's here, but we'll go through this. So we have just a few more lectures on pre-stressed concrete, right? We're in the middle of deflections. Calculating long-term deflections is what we're doing now, and so we'll kind of finish up that discussion on deflections. It turns out it's really hard to predict long-term deflections of pre-stressed members, okay? But there's ways that we can account for it, and we'll do our best guess, right? And all of concrete's a big guess, right? Everything in concrete's a big guess. And so you really know that it's a real big guess when the ACI gets to a point and goes, yeah, this is really hard. Like, they're not even gonna try. And you'll see that they don't really try. They'll say, yeah, we don't know. Nobody knows. But you should account for it. But we'll look at that, how to do this long-term deflection. Last time we talked about immediate deflections and crack deflections. We'll do long-term deflections. Then we're gonna go into creep and talk about how you calculate creep. Again, nobody knows, and so it's just a big guess, and then ACI doesn't provide a lot of guidance. They just say, hey, go, you need to account for it. So we'll kind of cover that and talk about the methods. The PCI design manual actually does cover it in a little bit more detail and give you some examples and stuff, so we'll look at those. So then after that, we have composite construction, which is where they have pre-stressed member, where you put a composite slab on top that isn't pre-stressed, and you can imagine that would cause more load cases to test, right? You have your pre-stressed member in its initial state, and then you come in and you put a dead load of concrete on top of it that can't carry its own weight, and then that comes to strength, and then it becomes composite, and then the two act together. It gets a little complicated, but a day or two of lectures there, and that's all the stuff that I'm gonna teach you. Starting next Friday, Kyle Boyd is gonna lecture live via like Teams, I think, in here. We did this a couple of years ago, and he's gonna basically has 4 lectures to talk about post-tension floor design. Kind of from he's out of the Denver, or he used to be out of the Denver area, and they did like every building they did had post-tension floor design. So, and then before he worked as a structural engineer, he was actually worked for Baker Construction, where he built these things, and so he's got like his knowledge on it is just phenomenal. So he's going to teach us four classes. I talked to him yesterday. He sounded absolutely terrible. He's got COVID. A breakthrough case of the COVID. It actually made it into his lungs and everything, and then it was just, I could barely understand the guy. It was terrible, but hopefully he all recovers. And then his wife didn't get it, because she was vaccinated, and she was around all the time. How are you feeling, Matthew? Good. So good. So good? Not just a little bit, but really good. Yeah, good. Monday, what a crazy day, huh? 3 classes that morning got canceled. Freaking awesome, right? It's day off. It's day off. Yep. Okay, so let's dive into this long-term deflection. So that's really good. So a few years ago, Dylan Nisbet and I, 4 years ago, he did for his professional paper, he at the end of his master's, he put together notes on how to do post-tension floor design stuff, and he worked really closely with Kyle Boyd when he did that. And now, I don't know if you guys met, Dylan was over at the job fair, so if you went to the career fair, he was there, he works for KPFF, and he's like the go-to guy in the Boise area doing post-tension floor design, so he's learned from it. Yes, Jake?
Did you guys have any problems when you built that bridge of all of the members being different?
We did, Jake. We did.
I was talking to my dad, he said that they did a roof on a building, and it was double T's, and he said they had a hell of a time with it.
Yeah. Let me see if I got some pictures of it here.
I think he took pictures.
I think I did, right? Went to the Lookout this last weekend. It's sweet up there. Look at that. Stayed in there. And, yeah. Garnet Mountain Lookout. You can rent the Lookouts. Yeah, don't tell anyone. It's really sweet. It's really sweet. I'm not telling you. I just said that I'm going to tell you. This Garnet Mountain, so like if you're driving up Big Sky, towards Big Sky, and then right around Storm Castle, you look up, there's a lookout up there.
Oh, Garnet.
Garnet, yeah. What?
Isn't that a Forest Service?
It's a Forest Service car, yeah.
How'd you get that thing?
6 months ago at 9 o'clock in the morning, me and a couple friends sat there hitting book, like, to snag it. Yeah.
That's awesome.
Isn't it sweet?
That's pretty nice.
Damn right it's nice. Don't tell anybody. Look at the sunset. Sun setting up there. It's a really cool experience. It used to be $30 a night. Now it's 6 year. Yeah, they doubled the prices of it and stuff, but it's worth every penny of it. That's my wife. Yeah. Picture time. It's picture time at the Berries. Okay. When was that? September 13th. What was it? When was it?
That was the second one.
The second one, right?
Pictures both mornings.
I don't know if I got them both mornings.
But you're past
Was it the 13th though? Is that when it was?
the-
Oh, there it is, right there. All right. That's the morning of. Maybe I didn't take pictures of it. Oh, second day. So yeah, so these guys are all coming in. So each one of these are hollow core. So these things have, you can't see them here, but there's big circles right there that run the whole length. And the reason that concrete there isn't doing anything, and so it's not really carrying any load, so it just makes them a lot lighter. These were 44,000 pounds a piece. That's with it hollow, and so if they weren't hollow, they'd be way more. And so then you can see the tendons, kind of the pre-stressed tendons there, and then a couple up at the top, that's what those dots are. And so they fly them in and set them next to each other. And they're all pre-stressed, and they're all going through different deflections. And Jake's question is, did they maybe not line up? And the answer is they definitely did not line up. It was a really cool process to see them go in. But once they were there, here we are. So this is what they were doing. So there were like, this one was lined up with that one, so there's a big, like, shelf right there. And so, to me, it was a little weird. How they tested to see whether or not it was level enough is the inspector, this guy, would just come over, looks like he's drinking a beer. He'd go over with a beer, and he would go like this. He'd go like this, and he'd just kind of kick it. And if it was like if he felt like there was too much, he's like, oh, you gotta adjust this one. And they go over this. Yep. I thought they'd have like some sort of tool with a level and the numbers. Nope, they just that guy just drinking a beer, comes over and kicks it. So what's interesting is, and like this is, they've done this before. They've all done this before. Because actually, cast into the pre-stressed members were these little holes. You can just see it right there. There's a hole specifically made that you could thread into. They have this rod right here that can thread into that, specifically for adjusting the heights of these things as they go. So what they do is they start in the middle, and so in this case, this one was low. So this one was lower than these two. And so what they do is they set up a little beam that spans across, and they attach that beam to this member right here, and then there's a jack over here. So this guy's going to start jacking this up, and as he jacks that up, it pushes down on these two and pulls this one up. And then it'll get to a certain point, so when then those things get level, then they have little shear tabs, or they have little tabs, metal tabs inside there, and they go in and weld those tabs and then kind of hold it in place. So they kind of jack it like that, get it to, where this guy can kick it, where it's not separated, and then they weld it together in those locations, and then they release it. But then, what's that?
He said that too. He's like, yeah, they're all welded together. And I was like, wow.
Yeah, if you look down in there, I don't know if I got a picture of looking down in there. There's this one's got an embedded plate, and this one's got an embedded plate. They bring them next to each other. They put a plate on top of it and weld all around that plate and kind of hold it together. And then this is what they came back and filled with concrete afterwards on top of that. So they're kind of holding it all together. Is those shear tabs and that. But then you can imagine, right, in the process of pulling this one up, they pushed these two down, right? And so then they have to they start chasing their tail a little bit, because they're now like, okay, well now we gotta go over this one, and because now this one's gonna be too low compared to that, and so you just work your way around it. So they kind of started at the middle, worked their way out one direction, start at the middle, work their way out the other direction. So that's how they accounted for it. So built into these things are some internal stresses. Like now this beam, that beam right there has stresses in it. In its natural state, without any load on it, it's carrying load, right? Because they had to bend it down and you weld it into place, so it actually has bending stresses on, internal built into it. But then what was cool is that, as soon as we show up on the job site, if I were in charge of this, they'd be like, well, shit. First of all, those beams all they would have been too long or too short. If I were building it, right? It wouldn't have been close, and it would have been sideways and all this other shit. But immediately I would have gone to the same, well, they didn't line up. Well, shit. Uh-oh, right? But immediately before, while they were still placing it, they're not even done placing it. Or they're done. Yeah, they're not even done placing them yet, see? still have to put the other ones on there. And so, like, while they're still flying in those other beams, they're over there adjusting the heights of them and stuff. It was just like, and again, they're planning on this and had those things. Because for rideability, you can't have, you know, the beams on level as you drive along. So I think that's, they guess, and then that, but that's just also, again, immediate deflections. But then hopefully from there on out, as things creep and move around, they're all tied together into one big unit at that point. And so if one starts creeping a certain way and the other, they're stuck together. So they're all gonna do it together. Yeah. They're on a ride together. You can see that, you can still the steel, these are the steel plates in there.
I don't think there's a plate up that side yet.
Yeah, and then they haven't put the plate on top. They put a plate on top and then weld around it, yeah.
They also like grinded the surface down. Obviously, they didn't get it level. Do they probably assume maybe some of that takes out the inconsistency?
Yep. So when they overcast. This is funny. Okay, so then they overcast it. They don't think I got any ground
Yeah,
pictures.
at the very end.
So here we are. So it's a really busy day, right? We did all this placement and they finished it all up. And then it was really, I mean, it's really intense. It was the end of like this big, like months-long project. And then this is my dinner, my celebratory dinner that night. It was just me. Everybody left. Everybody left. You son of a bitch. I tried to get people to stay. As I said to my wife, "Yep, just celebrating the big win today." Just me and my buddies. Like, I even tried. I was like, "Kirsten, you want to stay here, Kirsten? The students, you guys want to stay? Want to have dinner? Some of the contractors, you guys want to go do something?" They're like, "No, we got shit going on." And then it was just me eating by myself. And so they overcast the top and they come back and ground the surface, and then they would actually, so when they were grinding the surface, they were coming back and that was taking some of it out too. And in some cases where the guy's technique of kicking it wasn't perfect, it was still, even after they cast it, it was still a little lump, and so they would actually grind the top surface off the pre-stress member too. So they would make sure that it was like, again, so then the guy could come over and, you know, tap it a little bit more until it got to a point. So they would actually grind the top of the pre-stress member off. I don't know if I've got any pictures of that. They didn't do a great job. Right? Yeah, because in cases like this, they didn't go, they're supposed to go like 5/8 of an inch up. Just over or half an inch, 3/8, 3/8?
3/8 to a half.
3/8, and they only want a 1/4 inch. And then so then the way this UHPC works is it bubbles up to the top, and then they come back and grind the surface off. They didn't provide enough cover there, so when they ground it obviously picked up a lot of those bubbles. But then they put epoxy down afterwards. They tested the strengths yesterday, and they were like 17, 18 KSI. But then they came back and they epoxied the top of it afterwards. They put down like an epoxy. This is the crew. I go, "You guys want to get a picture?" And he go, "We don't do pictures." And I was like, "Well, as an academic, I do pictures. So can I get a picture?" He goes, "Nope. I'm not gonna." He goes, "I'm not gonna call people over here for a picture." He's like, "I'm not doing it." And so I caught him. They were going to lunch, and I caught him. I ran over there and like, took a picture. Yeah. Okay. Okay. So let's go back to this. Great question. Long-term deflection. So how do we account for these things? What we're going to do, we're going to rely on what MDT or what PCI does. But we'll get to that. Let's just kind of revisit why it is that this is important. So while I'm distracted right now, since we're having to talk about it, I keep meaning to remind you guys about this. Like, what always shocked me when you walk up these stairs. Do you guys ever look down at the stairs, like coming up the main hall, and how they're like old granite? It's all like divoted from 100 years of students walking up, just going to class. Right? I always need to mention that to you, because it's rare that I teach up here, but every time I do teach up on like the 3rd floor, I always notice, 3rd or 4th floor, I always look at that and just like, the history in this building is so sweet. Like 100 years of engineering students walking up those exact stairs, wearing down the granite as they go up, right? Phenomenal. So you're not alone. This feeling you have, you share it with 100 years of people in the past. And then what's also crazy too is, if you look, the stairs are all messed up there. You ever looked at that? The original stairs, there was a landing, but then to have it line up with Cobley, they kind of added this fake stairs on top of it. So you only get that wear down for like the first flight that you go up, and then after that it gets weird. It gets into the other one. Okay, so creep can cause upward or downward deflections. This is just why it's difficult. This is depending on C line. Where's the C line at? Where's the effective compression force act? Shrinkage causes downward deflection. Relaxation. Steel causes downward deflections. And you'll see, right, obviously this is all tied to creep. Deflections, long-term deflections are all tied to losses, right? If these things are happening, then you're getting losses, which are messing with all of your deflections as well. Yeah, Young's modulus changes with time. Right? Concrete compression strength changes, so then your Young's modulus changes, right? So that's all messed up. Tied to pre-stress losses. Pre-stress change. And then I just throw this, it's a crapshoot. Right? We don't know. It's just a guess. We're just guessing, right? And ACI even acknowledges, it's like, oh, yeah, this is really hard. We don't know how to do it either. Okay, so what is the code? How does the code handle it? We've got ACI. They say these are important. Must account for them. Okay, that's it. They don't tell you. They don't tell you how to do it. They say, yep, these are important. You must account for them. The one thing that they do is they point to references. And you'll see that it's weird. I always find it weird that ACI does this, but they do. They just right in the middle of it. They're like, this is really hard. You definitely need to account for this. This is outside of our specialty. So we're not going to tell you how to do it. Just do it, right? Go do it. I've seen an ASCE will do it on occasions. ASCE does it for progressive collapse. They'll say, look, you should really be concerned about progressive collapse in your structure. And then they're silent. They don't tell you how to do it, right? But the codes do that sometimes. And at least they're being honest there. This is 24.2.4.2. That's where they point to references. AASHTO. We're going to get into what AASHTO is later, but that is the highway design. American Association of State Highway Transportation Officials, AASHTO. But they provide an okay method of calculating deflections. Tied closely to pre-stress losses. And it is prescriptive and empirical. Right? Like most concrete codes. Right? Most concrete codes are prescriptive and empirical. Right? But it's very follow this procedure. Okay? And just based off of old test results. And then the final method that we're going to use is PCI, design manual. There's 5.8.4 in that PCI design manual. And what they have is multipliers. And then this actually comes from one of the references in ACI. We are using this. So you could use and I guess the point of this last statement is you can use this PCI design manual method for ACI, right? ACI points to one of the references, it's like from 1970s or something like that. They say, go see this reference. That reference was adopted by the PCI design manual. It has these things called these multipliers for accounting for these deflections. We'll see it at play here in a second. We'll go through in detail what the PCI design manual does. But it is based off of the same reference that ACI points to. So in theory, it would be allowed by ACI. So it'd be allowed by the code, and you can do it this way. The questions like this, like, what do you do in the real world, would be a perfect thing to ask Kyle when he teaches in a week and a half or whatever. Say, like, how do you account for pre-stress loss, or how do you predict your long-term deflections of your post-tension members? And they probably have some method for doing it. They have, yep, go ahead.
I was just saying, did you ever also decide what you were doing test-wise, like
No, I mean,
when or in class, or how you're gonna do the class?
I haven't thought. I mean, it'll probably be a class. We can all go early, is that correct?
Yes.
We could all go early, so we'll plan to go. Is there a class in here before? There is a class in here before, so we could go. I'll find a room for us, and we'll start early. Maybe we could pick a time right now. You want to pick a time? So Kyle's going to start next Friday, the 22nd. And then he's going to go 25th, 27th, and 29th. And so you can't do it on Halloween this year. It's a Sunday. But we can do it anytime this week. Any preferences? The week of the 1st, 2nd, 3rd, 4th, 5th, Tuesday?
We can't do it on Tuesday.
Oh, we can't, because we're not allowed to do that anymore. But
I was just saying because I have to work, but
no,
I don't know if they're.
no, yeah, it's your fault. So, no, yeah, no, you're one of those workers, Amanda. No, but we need to keep it at the same time. So, any preferences there?
No.
I like Wednesday.
Okay.
Preferably not Monday, just Monday.
Yeah, let's do Wednesday. Let's do Wednesday the 3rd. Maybe start half an hour early. That's good. I like that. The 3rd. Okay, and we'll have completed everything post-tension, and post-tension floor design will be done by then. We'll be done with the stuff here. It'll be
So 9:30.
Yep, starting at 9:30. Yep, and I'll make it I'll make it work so that you can do it in an hour and a half. It's gonna have to be conceptual, right? You can't be doing all these calculations by hand. Calculate the shear capacity of this beam using BCI and BCW methodology, right? Like, can't happen. Could be funny. It'd be funny from my perspective. At every location along the length of the beam, by hand, calculate this value.
Maybe do it on TI Inspire or something.
Yeah. Okay, so this is what the PCI design manual says. So I don't know if it says that. Yeah, so this is the PCI design manual. We should make that clear. Right, this is what they say. So this might be, if you remember, if you've taken the advanced concrete, this is what they use for calculating long-term deflections. But this does not work, and that's what the statement says. This doesn't work for pre-stress. There is no corresponding ratio for pre-stress concrete. Okay, so here's their statement. Determination of long-term cambers and deflections in precast pre-stress components is somewhat more complex because of the effects of pre-stress. The loss of pre-stress over time, the strengthening of the concrete after release of pre-stress, the camber deflection is important not only at the initial final stages, but also direction, which occurs some immediate stages, usually from 30 to 60 days. And so you have all, your concrete strength is changing properties, you have all this stuff, other stuff going on. at the period of time multiplying the initial so it's customary by multiplying the initial calculated cambers by some factor, usually based on experience of the designer. So it's very open-ended. To properly use these multipliers, the upward and downward components of the initial calculated camber should be separated in order to take into account the effects of loss of prestressors, which only affect the upward component. Table 5.8.2 provides suggested multipliers that can be used as a guide in estimating the long-term deflection. So that's what this is. So this is their method. Basically says you calculate initial cambers and initial deflections, and then under these different states, you apply these different factors to the deflections that you calculate. So you calculate the immediate deflections, under the at initial stages or at erection, and then at the final stages, you calculate the immediate deflections, and then you multiply them by these factors to calculate what the long-term deflections are going to be. It's very straightforward. A very straightforward method for calculating these things. It's very, obviously very empirical, where you're just like, oh, I predict the deflection is going to be 1 inch. My final stage is going to be 1 inch down, but I'm going to take that 1 inch and I'm going to multiply it by 2.7. That's how much it's really going to deflect, right? But then those multipliers go. You have the upward deflections; they get multiplied by certain factors, but you also got the downward deflections, and they get multiplied by certain factors. And then, so it's a little bit of a bookkeeping issue when you go through this. Example 5.8.4.1 goes through how to do that. So I'm not going to go through that now, but when it comes time, in the homework that I gave you, you have to calculate the cambers, the long-term cambers in the calculation there. You have to calculate the long-term cambers. You'll follow this process for doing it. Okay, almost just directly like this. And you'll predict it, and then you can kind of, so when you get to that stage, just kind of slowly go through this example and then apply that to the example that you're doing as well. Okay? So that's how we're going to do it. Like I said, pretty straightforward. And just a big guess. So let's, is there an extra homework somewhere there? All right, homework 5. So what are you doing in this one? Okay? So you're going to go find in the PCI design manual a 40 IT40 on a 48-foot span. You got there? Anybody else not get this? Jacob to me, Jake. It's like Gregorius. There you go. 40 verify the following: use an FPI of 0.9 FPU, an FPI of 2/3 FPU, and an FPE of 0.8 FPI. Okay, so use those values in your calculations, and then what you're going to do, you have all these programs, okay, and you're going to go through and you're going to make sure that that load that they give you in that table actually works. Okay, so you're going to look at all the service conditions to begin with, and make sure that with your previous programs that you have set up, you're going to make sure that all your stresses are within the limits that are allowed in there. Then you're going to look at your ultimate load and make sure that your ultimate load works in that case, and then you're going to look at your shear capacity and make sure that it all works. Okay, and then after that, so that's part A. So this is a long assignment, right? To go through and apply all of your codes to all these things. But also, you've made those codes already, so you don't have to remake them. You just have to change the values that are going in there, okay? And then you're going to calculate the anticipated camber direction, include only the deflections from pre-stressing and self-weight in this calculation, and use the PCI multiplier approach to account for the time dependent effects. Compare what you get to the value indicated in the load tables for the speed. So in the load tables, there are predicted cambers. And so see if your predicted camber ends up being the same as their predicted camber. I think they do. I think you can get them right there, okay? And then calculate the estimated long-term camber for this being used PCI multiplier approach. And again, compare your results to the values provided in the table. Compare the estimate will include only the deflections with the dead load, self-weight, and pre-stressing. Do not include the live load in this estimate. So those cambers don't have built into it the live load deflections, right? They're kind of saying this is what our beam looks like, this is what it's going to deflect as, and then you put whatever loads you want on there, and it's going to deflect a certain amount. But we're not calculating those deflections. It just gives you the cambers. So you're just checking to see what the state of the beam is going to be without the live load applied to it. Okay? And then those numbers you should get pretty dang close to what are in those tables. Okay? And then so you're just kind of verifying that their design methodology actually works. So you just take their loads, you take all the properties from their beams, put their loads on it, and then just make sure that it works for those given loads. And then calculate the pre-stress losses using PCI method. So that's the next thing we're talking about is PCI. methods. Obviously, if things come up in that, solving that, come and see me and we'll go through that. But it is a lot going on. Also, I need to give you back your last 2 homeworks, which were, we gotta make sure that you did those right. I think for the most part, you guys know you did them right because you worked together and all that other stuff. But still, I'll give you feedback and just say, because you don't want to do this assignment without knowing you did the other assignment correctly. So this is due next Friday. And so maybe by Friday, I'll try to get you your other homeworks back so you know that you did it right. So you can apply those codes that you made to this guy. Okay. All right. Pre-stress losses. So what happens in pre-stress? We've mentioned this lots of time, but we haven't once talked about how to account for it or how to do it. All we've done with pre-stress losses thus far is I give you FPI and I give you FPE. So I just tell you what the effective pre-stressing force is. We don't talk about how you go about actually calculating it. So let's talk about actually calculating. So what we're doing, just to refresh your memory, you're going from FPJ, right? That's the jacking pre-stressing stress. That's going to FPI, right? That's the initial pre-stressing force, right? Because you get losses between your jacking and your initial pre-stressing forces due to various things. And then that's going to FPE. Okay, that's kind of what the journey is if I give you the jacking pre-stressing force, that's going to the initial pre-stressing force, which is then going to your effective pre-stressing force. Okay. These are covered in PCI, chapter 5.7, covers this topic. ACI, it's briefly covered in 20.3.2.6. And then ACI also has a special provision, 432R16, which is focused primarily on pre-stress losses. Okay. So just got to give you the code references as we move forward that if you want to look up more, we're going to go through each of these in a few minutes, but they all have their own positives and shortcomings. Okay, AASHTO also has a section. I don't know. Let's add an AASHTO here. AASHTO also talks about it. Offhand, I don't remember what that reference is. Okay, so these things came from Stanton's notes, this table right here. So he talks about, I think this falls into the very similar category. I picture Stanton drinking a beer, making this table. There's no quantifiable thing. It's just like, it's how he feels, it's qualified, how he feels that these things are important, okay? So these are causes of losses, okay? Thermal during casting. I don't even know what that one is necessarily. Oh, I don't know what that one is. I don't know what that one is, okay? So it expands and contracts during casting.
Like the heat of the concrete.
The heat of the concrete.
Like,
but how's that causing a loss? Like maybe it was warm when it did it, and then it got cold after time and it shrank up. I'll buy that. I buy that.
That's why it's 1x.
It's only 1x. Yes, Dan says it's only 1x. So this is not that big of a deal. And I'm not exactly sure that one. I think maybe in his notes he talks about it in a little more detail. I haven't reviewed those in a while. Elastic shortening. It gets a 4x. It's a 4x. Okay. And this is you only see it in pre-tension. You don't see it post-tension. The reason you see it pre-stressing is because you stretch the steel, you cast concrete around it, you cut it, and it shrinks in immediately. And when it does that, your steel shortens, and so you get pre-stress losses immediately from that. And you'll get that for pre-tension. You don't get that for post-tensioning, because post-tensioning, you have the concrete's cast, has ductwork in it, you start pulling on that member, and then as you're pulling on it, it's shortening as you're going along. So it's not a loss. It's like you're pushing against your concrete, and while you're pushing against your concrete, it's kind of squishing up. And then you put your anchor on there, and you stop pulling, and it just stays in that position. So it's not, you still get elastic shortening, but when you're jacking it up, you don't actually get a loss, and so it doesn't show up here at all. Okay, shrinkage, double X. You get a double X in that case, and right, shrinkage is when concrete just shrinks over time. Yeah, so it's just the concrete drying out, and then also the chemical process between the cement particles, it just shrinks a little bit. It's called autogeneous shrinking. It just kind of shrinks, the mass kind of changes, it becomes more dense as it goes along, and it gets smaller. Creep, 4 X's, both directions, right? Concrete creeps over time. And all these things are hard to predict, right? Like concrete shrinkage, right? How much is your concrete gonna shrink? I don't know, sometimes we're just lucky if we get the strength that we want, right? Like we're just trying to guess on the strength. How the hell are we gonna predict what the shrinkage is? It's just a freaking guess, right? It's just a big guess.
And all that varies with like your conditions.
It varies with the humidity outside and how much rain you get, right? It varies with all how much wind you're seeing, how much exposure you have, right? Creep, again, I can barely predict the concrete strength. I mean, real world, you've been in real world a long time, something, like how often do you get the exact strengths that you aim for?
Most of the time, depends on
You
your supplier,
do?
but we've had to do quite a bit of shrinkage testing.
Do you really?
It's kind of a crapshoot.
What do you do? Do you have the testing equipment for that, where you control the humidity and all that
Or,
stuff?
no, I'll cast the beam, but we'll send it out to the lab.
Oh, you said it to lab, yeah. Because we tried to do it on our end, we just can't do it. We don't have the, because you have to put it in a humidity controlled room and test and stuff. It's just hard to predict. Creep, the same thing. I don't know, right? It's like, you know, when Matt, do you guys end up with concrete strength? I mean, you always meet the minimum strength, but you don't get exactly 4,000. When you order 4,000 concrete, you don't get 4,000 concrete, do you? No, right? You get like 6,000 or 7,000 or 4, you know, usually get at least their 4,000, right? I mean, and so creep, again, what the hell? I don't know what it's going to be, right? But it's going to make a big difference, right? Steel, there's a friction losses, and what that is right, it only shows up in post-tensioning. If you're post-tensioning, it's going like this, right? It's like going up and down as you go across the thing. Well, when you go to stretch it, you pull only from one end, right? So you yank it from one end. Well, every time it touches the concrete, you're pulling against, it's friction against that. So by the time you get to the end, it's not the same that you pulled on this end, if that makes sense, right? Like I pull on this end and you lose friction along that whole way. So what makes it to the anchor on the other end is not what you pulled on this end. And that's the loss due to friction. You don't get that in pre-stressing, obviously, right? Because it's already pre-pulled when there's nothing there, and then it shrinks up. Okay. So friction losses can be a big deal. Steel anchorage slip, obviously, you're gonna get. I like the X, 4 X's, right? Like if you have your pre-stressing and then you put the anchor there and then the anchor fails, then we're out in the 4 X's, right? Or like where maybe like they should put like 10 X's if the anchor failed, right? But obviously you don't get that. So this is you're using your jack and you're pulling the concrete and you have an anchor right here, and then you release it and then it embeds into that anchor and then sits there. If that anchor fails or if it moves a little bit or whatever, you get pre-stress losses in that case. Okay, and then relaxation, that's where you steel, right? Just you hold. It's the opposite of creep. Like creep is squishing and compression under sustained load. Relaxation is under sustained load. It elongates, right? And so steel can be that. The reason it's only 1X now, it used to be a bigger deal, but now they have low relaxation strands that they've kind of. We talked about this before, where they condition the steel in a certain way so we get less of that. Okay, I found this. This is not in your notes, but this is. I thought this was kind of nice. The pre-stress losses can be broken into kind of 2 different categories. Immediate. I'll post these under completed notes if you guys want to track this thing down. But pre-stress losses can be broken into immediate and time dependent. Right, immediate, elastic, friction, and anchorage slip. Those all happen like immediately, right? But then the time dependent creep, shrinkage, and relaxation. I thought it was nice because I didn't really parse that out before. Here's another. This one's from Stanton. This one is in your notes. So this is kind of showing over time what happens, and this kind of says the same stuff as this over here, right? This is relaxation thermal, which we're not exactly sure that is, but between jacking and when you release it, you get a little relaxation in your strands or whatever, right? I can imagine that. If you're doing pre-stressing, you stretch it, you're holding it there, waiting to cast it, you cast it, and then in that process, you get relaxation in your strand. I can see getting loss of tendon stress during that. I'm not exactly, again, I'm not sure what the thermal is. But then immediately, concrete's cast, release, immediately shrinks in. That's what that loss is right there. I knew that was gonna happen. Can't afford to fall anymore. Okay? Elastic shortening, boom, it shrinks up. And then over time, you get shrinkage creep and relaxation. And it comes out to there until you hit what your service conditions are. So when you do a design, I should mention too, that this, where it kind of flattens out, this is, Stan talks about this, this is 5 years. Okay, where that service, so when you're doing design and you're saying, well, my FPI, my initial pre-stressing force for my initial design, and my pop-up, and I'm worried about that, and then you go, okay, under service conditions, my FPE is gonna be, a reduced amount. You're talking about 5 years down the road what that amount's gonna be. It's gonna be more, it's gonna be FPI immediately, right? And then just slowly over time, that FPI is gonna go down to FPE, right? So, I would say that this is FPI right here, just to put that into perspective, right? And then this is what FPE is, right? In our design naming scheme, right? And that's happening because of the shrinkage creep and relaxation over time. So that's the time kind of stuff. And then, so you're designing for about 5 years, and then after that, he shows the live load going up and down, because the live loads come and go over time, and so you're gonna get the stresses are gonna increase and decrease as those loads are applied. Okay. The other one that came up as I was going through this, and I think Kyle talks about it when he visits with us, is this idea of wobble losses. It's my favorite type of loss, just because of the name, right? Wobble losses. Right? You really don't sound like you know what you're talking about, or you sound like you don't know what you're talking about when you're talking about pre-stressing members. But wobble losses are tied to friction losses, and I Googled it. I know, like I said, I think Kyle throws that wobble losses around quite a bit. But say if my desired profile looks like this, it shows up in post-tensioning, if that's what I really want it to look like, but in the field, you only put supports at certain locations along the length, right? So you have to support it when there's no concrete around it, right? In the field, imagine all those tubes that we saw in that video, or in those pictures before posted to the floor, right? They're just kind of like going like this all over the place. Well, you have to put that in the desired profile, so you put little supports, little chairs all over the place. And so in between those chairs, your post-tensioning can sag in between those chairs. So that's what this is showing, it's just it's sagging between the chairs. So it's actually, you want that, but it's actually kind of wobbling, if you will, as you go along the length. And when you go to pull on that, you get extra losses because of that, because it's the more friction. There's more friction in there than you originally intended. And so you can pick up some things. And certain methods they parse out wobble losses. They talk about those being separate. So I threw these aren't in yours either. I just kind of added this recently. But like I said, Kyle should mention the wobble losses at some point. Okay, that's good. So like the next topic we're going to talk about, well, it's really hard to calculate these things, but what happens if you don't calculate it right? Turns out not a lot, right? It's mostly a service condition, serviceability issue. It's not really a safety issue. If you it's important to account for them, but if you mess them up, people don't die. Okay, and so it's not that big a deal. We'll talk about these effects, and then we'll talk about how you go about calculating them. Right? We'll look at the methods: ACI, what they say; PCI method, what they say; AASHTO, what they say; the ACI 432 document, what they say. Cool, See you guys Friday.